Hello, and welcome back to the course on Physics for Engineers. This is now the last lesson for this chapter. So before we proceed, let us review some of the concepts that we have discussed in the previous lessons and chapters. So in linear dynamics, we discussed about Newton's second law of motion, wherein it is actually related to the change in linear momentum or the impulse. So the net force, this is the equivalent of this is just the equivalent of mass times acceleration. It's just the change in momentum over the change in time. So similarly, we will explore a similar relationship in the case of angular momentum. So angular momentum is the rotational analog of momentum. So it's the measure of the difficulty to stop a rotating object. In a similar manner for linear momentum, which is just a measure of the difficulty to stop a moving object. So here, a rotating object. So if an object gains angular momentum, then that object is now very hard to rotate. So if you have an object, it has a mass and it's moving with the velocity v in a circle. So it has mass and it has velocity, so it has a linear momentum p, and it's moving or it's orbiting up an axis of rotation, a distance r from the object. So in that case, the angular momentum of that object is just given by the cross product of the radius vector r and the momentum vector p. So in this case, we usually call this type of momentum as orbital angular momentum. This the object is orbiting around the axis of rotation. The magnitude of this is, of course, mvr. For this case, the angle between the r vector and the p vector is 90 degrees. So it's just rp, where p is mass times velocity. So mvr or r and v. Now, another type of angular momentum is what we call spin angular momentum, and it's related to the spin of the particle. So if the particle is spinning with an angular velocity of omega and it has a moment of inertia I, then its angular momentum is I times omega. So in advanced physics courses, the symbol for this is actually S, because this is spin angular momentum, but in the reference that we are using, Young and Friedman, University Physics by Young and Friedman, we will still use L. But there are actually two types of angular momentum. So the total angular momentum is then the vector sum of the orbital plus the spin angular momentum. Okay, so this is now the rotational analog of Newton's second law of motion in terms of the impulse of the change in momentum. So similarly, if the summation of force is dp dt, the derivative of the time derivative of linear momentum is the force, then the time derivative of the angular momentum is also the torque, and it's equal to I times alpha. This is Newton's second law, rotational analog of Newton's second law of motion. Okay, from linear dynamics, a change in linear momentum will create a force. So in the same manner, in the rotational version, a change in angular momentum will also create a torque, will create rotation. So if you change your angular momentum, that will actually create a torque. There will be a net torque on the system. So similarly with linear momentum, angular momentum is also conserved in the event that there is no net torque acting on the system. So in linear momentum, if there's no net force acting on the system, then angular momentum is conserved. So in a similar manner, if the net torque is zero, then the angular momentum is conserved, or that means that the initial angular momentum is equal to the final angular momentum of the system. So It could be a summation of the angular momentums of different masses or different bodies or different objects. So the angular momentum here that is conserved is the angular momentum of the system of rotating bodies. If there are many rotating bodies in the system, then you have to add all of their angular momenta. Okay, a consequence of conservation of angular momentum is a motion called precession. So this is the motion when the axis of a rotating body changes direction. So precession. There are many objects that actually undergo this motion, and in general they are called a gyroscope. So example is the Earth. The Earth is a giant gyroscope. It's spinning around its axis, and its axis is actually changing. After every thousands of years, the axis of the Earth is actually precessing. So this is an example, a classic example of demonstration of a gyroscope or a precession. So you have a flywheel here. So when the flywheel and its axis, so there's a flywheel, there's an axis, it's connected to a pivot point. So when it's stationary, this will just fall to the table or on the surface. But if you try to rotate the flywheel, you will notice that its axis will actually also rotate. So its direction, its axis of rotation of the flywheel will also rotate. So that is an example of precession, and that is a consequence of the conservation of angular momentum. So a spinning top is also an example of a gyroscope. So that one. Okay. So let's now have an example for this topic. So we have here, we're asked to find the magnitude of the angular momentum of the second hand of the clock about an axis through the center of the clock. So the angular momentum of an analog clock. This is an analog clock, this is not a digital clock. The clock hand has a length of 15 centimeters and mass of 6 grams. So we have a clock. And this is the axis of rotation. This is the second hand of the clock. We are asked to find the clock. The length is, it has a length L, which is 15 centimeters, or in standard units, that is 0.15 meters. And its mass is 6 grams, or in standard units, that is 0.006 kilograms. Okay. Take the second hand to be a slender rod. So assuming, actually this is not a very good assumption, but let's just assume that is a slender rod rotating at constant angular velocity. So the moment of inertia of a slender rod rotated not at the center of the rod but at the edge of the rod is 1/3 mass of the rod times the length of the rod squared. So that's the moment of inertia. Okay. So how do we find the angular momentum in this case? So the angular momentum is just the moment of inertia times the angular frequency. So the moment of inertia is 1/3 mr squared. Then you have omega. So you have 1/3. The mass is 0.006. The length is 0.15. Square that one. Okay. What is the angular velocity of the second hand of the clock? Its angular velocity is actually, can you guess? It's actually fixed. All clocks have the same. All second hands of all clocks have the same angular velocity. It's actually 1 revolution per 60 seconds. And you need to convert actually this into radians. So you need a multiplication factor of 1 revolution is, or no, I will just use directly. 1 revolution is 2 pi radians. So you have 2 pi radians. 2 pi radians, that's 1 revolution. So for a second clock, that's actually 60 seconds or 1 minute. So that's the omega, angular velocity of the second hand of the clock. How about the angular velocity of the hour hand, or the minute hand, or the hour hand. So one revolution over that one, 12 hours. One revolution over 1 hour for the minute hand. Okay. So doing this will give you a value of 4.71 times 10 to the negative 6 kilogram meter squared per second. So the same with torque. There's no special unit for angular momentum. It's just mass kilogram times momentum, which is meter squared per second. Sorry, R times P, position times momentum. Position is meters, momentum is mass times velocity, so kilogram meter per second. So you will have kilogram meter squared per second. Okay. So let's have another example. So this is called a Ballerina professor. So you have an acrobatic physics professor. He stands at the center of a turntable. So this table here is a turntable. It can turn around. Holding his arms extended horizontally with a 5 kilogram dumbbell in each hand. So this is a 5 kilogram dumbbell. This is another 5 kilogram dumbbell. He is set rotating about a vertical axis, making one revolution in 2 seconds. Okay, find the prof's new angular velocity if he pulls the dumbbell into his stomach, like this. So his moment of inertia without the dumbbells is 3 kilogram meter squared when his arms are outstretched. And his moment of inertia becomes 2.2 kilogram meter squared when his hands are at his stomach. So the dumbbells are 1 meter apart, 1 meter from the axis initially. So this distance, this is the axis of rotation, and the dumbbells are 1 meter. So that's a very long arm. That's 1 meter. That's also 1 meter. And when initially, and when he is now pulls the dumbbells into his stomach, the distance now is that one, 0.2 meters. Okay. So the given values are the mass of the dumbbell, 5 kilograms. The initial radial distance of the dumbbell are 1 meter. They're actually the same for both the two dumbbells. And their final distance of the two dumbbells from the axis of rotation is 0.2 meters. Also given is the moment of inertia of the professor. Initial moment of inertia of the professor is given. It's 3 kilogram meters squared. And the final moment of inertia of the professor when he pulls the dumbbells towards his stomach is 2.2 kilogram meters squared. Okay. So this is a classic example of conservation of angular momentum. So I'm just gonna clear our table. So we need to know we have two systems here: the dumbbells and the professor. So the moment of inertia of the dumbbells will be m Ri squared Okay, sorry, I forgot to mention the initial angular velocity of the professor and the dumbbell is 1 revolution in 2 seconds. And of course, we are asked to find the final angular velocity. So for the dumbbells, The inertia, moment of inertia of the dumbbells is just a summation of mr squared. You have the mass of dumbbell 1 times the radial distance for dumbbell 1, which is just the same. They have the same value. So this will just give you 2 mass of the dumbbells out of the dumbbells inertia squared. Okay. I think I'm gonna go to my board mode. Okay. For the final in the moment of inertia of the dumbbells, the same formula, so you will get 2 mass of the dumbbells, but it's now a different radial distance. D final squared, where D final is now 0.2 meters. So if you calculate this mass of the dumbbells is 5 kilograms times 2, and then the radius, which is 1 meter, so you will actually get 10 kilogram meters squared. And for this, you will get 0.4 kilogram meters squared. So you now know their respective moment of inertia. The dumbbells, initial moment of inertia of the dumbbells, the final moment of inertia of the dumbbells, the initial moment of inertia of the professor, and the final moment of inertia of the professor. So we can now use the conservation of momentum equation. So the initial angular momentum of the system is equal to the final angular momentum of the system. The initial angular momentum of the system is the initial angular momentum of the professor, which is the initial moment of inertia of the professor times the initial moment of inertia plus the dumbbells. So in this case, they both have the same initial angular velocity, and they will also have the same final angular velocity because they are connected. The dumbbells and the professor are rotating at the same angular velocity. So you'll have for the professor final, then final angular velocity, and then the dumbbells the final angular velocity. So you already know the initial and final angular momentums of the professor and the dumbbells. You already know the initial angular velocity, 1 revolution per 2 seconds. So 1 revolution is 2 pi radians over 2 seconds. So 2 pi over 2, you will get pi radians per second. So this is actually pi radians per second, or 3.1416 radians per second. So the only unknown term here is this one. So you factor out the final omega, and you will get something like this. So that one. So this is now the final angular velocity. So if you substitute all of the values, you will get around 15.71 radians per second. So that way. By the way, please recheck all of my solutions, because maybe I made an error in my calculation. So please make sure to recheck and point that out to me if ever you found some mistakes. Okay, so that is for this problem for the ballerina professor. So you will notice that if the radial distance is large, the angular velocity is slow or small. But if the radial distance is small, the angular velocity is large. So in this case, in the second case, when the professor pulls the dumbbells towards his stomach, then it's actually turning very, very fast. So this is a classic, there's a classic physics demonstration for in science shows like this, or in science shows that you can find in science shows like this. Okay. So moving on to another example. So this is an example of a rotational collision. So problems involving conservation of angular momentum usually involve collision. In this case, we have a rotational version of that. So you have a rotating object A and a rotating object B. When they collide, they become one rotating object. So suppose flywheel A has a mass of 2 kilograms, radius 0.2 meters, an initial angular speed of 50 radians per second, and that clutch plate B has mass of 4 kilograms. So given ang ilang mass, and given ang radius, and given ang ilang initial angular velocities. So what happens? Find the final angular speed after the disks are pushed into contact. So it's still, the angular momentum in this case is conserved because there's no net torque. There's no, the forces that are acting here are acting on the center or on the axis of rotation. So they do not create any net torque. Okay, so I'm just gonna outline the solution for this problem. So conservation of momentum, initial momentum is equal to the final momentum. So initial momentum of A is the moment of inertia of A times the angular velocity of A, initial, plus initial momentum of B, moment of inertia in B, initial angular velocity of B, which is also given. It's 200 radians per second. So in the final, they're now one mass. So just add their moment of inertia of A plus moment of inertia of B, and then you have the final angular velocity of A and B. So to solve for the final angular velocity, it's just this one, the initial angular momentum of the system divided by the total total moment of inertia. So you will assume here that these two flywheels are solid cylinders. You assume that they are solid cylinders. You're calculating the moment of inertia. So you have the mass, you have the radius, you can calculate their moment of inertias given ang initial angular velocities of A and B. So you can now solve for the final angular velocity. So that's the idea. So I will just let you continue this one. So what about this question? What happens to the kinetic energy during this process? So if you will recall, in your linear momentum, conservation of linear momentum, collisions like this are called inelastic collisions. When the two objects colliding become one object. So inelastic collisions. And in inelastic collisions, the kinetic energy decreases after the collision. So the kinetic energy actually is not conserved. Only the angular momentum is conserved, but the kinetic energy is not conserved. It will actually decrease after the collision. Okay. So that is it for the end of this lesson, and basically the end of this chapter, the chapter on the kinematics and dynamics of rotational motion. So I will see you again on the chapters that will be assigned to me. So good luck for the quiz for chapter 6. And I will see you again in the next lessons. Goodbye.